Good afternoon, everyone, and thank you for attending our webinar today on high-performance, long-fiber, reinforced composite materials. Here's the agenda for today. We'll start out about talking about, basically defining what are long-fiber composites, and then we'll talk about the performance benefits of long-fiber reinforced materials, as well as their performance attributes. Then we'll get a little bit more specific, and we'll talk about a couple of different technologies, specifically long glass fiber composites and long carbon fiber reinforced composites. And then we'll talk about how we can further tailor those materials to meet application requirements. And then we'll talk a little bit about our company, PlastiComp, and how we work with our customers and partners. So let's start about defining thermoplastic composites. With our process, we use melt-processable thermoplastic materials. That means they can be melted and formed a number of different times, meaning they're recyclable. They're used commonly in the injection molding process and use those benefits of the injection molding process to bring advantages in structural performance as well as processing. They can also be used in profile extrusion for continuous profiles, including tubes and stock shapes, and then compression molding as well. So reinforcements are a cost-effective method to increase mechanical properties and lower cost thermoplastic polymers. They can be incorporated into any thermoplastic polymer, but typically we see the biggest boost in performance in mechanical properties with crystalline-based resins. Some of the different reinforcement options are particulate fillers, which don't lend a lot to mechanical properties beyond stiffness. Short chop fibers, which have moderate strength and stiffness increases, but don't lend themselves to toughness or impact resistance. And if you're really looking for a reinforcement that will increase stiffness and strength while improving the toughness of material, long fiber materials or thermoplastic composites are the way to go. There are also other types of continuous fiber and fabric mesh prepregs, but those are difficult to process and they're limited in geometries. So here are some of the different reinforcement fiber types, starting at the bottom, which are lower cost and don't lend themselves with as much mechanical property boost. Where we're going to spend most of our time is that center section. We're talking about glass and carbon. And there are some other reinforcements that are higher cost, like metal and metallized reinforcements that actually make the materials conductive as well. But again, we're going to stick in that range of glass and carbon typically for today's discussion. So what makes long fiber materials unique? Our materials are made with the pultrusion process. And if you look at the bottom right-hand corner of this slide, there are two pellets. For the longer pellet, this is made with a pultrusion process. And what we get with that is we get unidirectional fiber alignment throughout that pellet. Also, the pultrusion process gives us the capability to fully wet out or coat those fibers prior to the injection molding process. And that's important because that coating of the fibers protects them during the molding process and maintains fiber length in the final part, which leads to higher mechanical properties. If you look in that smaller pellet in the lower bottom right, that's a representation of a short chopped fiber pellet. And that's made by taking random orientated fibers, or random fibers, and dumping them into an extruder with thermoplastic material and mixing them. That mixing process actually shortens those fibers, and you typically would get less than a short, let's say 1 millimeter length fiber length in the final part, which leads to lower mechanical properties. So here's a representation of the pultrusion process. If you look over to the left, we start with fiber rovings, and they are pulled through an impregnation die. And you can see on the top there's an extruder or melt pump, which is pumping thermoplastic resin in. Again, the goal of this process is to coat the individual fibers, which leads to high mechanical properties and better surface appearance. Those strands are pulled and then brought to a pelletizer, and that pelletizer typically cuts our fibers to about 12 millimeters in length, which is optimal for injection molding processing as well as properties in the final part. Our composites can go anywhere from a 20 to 60% by weight fiber content, depending on the base resin that we use and the fiber type that we're using. So let's talk about the benefits of long fiber thermoplastics. First, stiffness. Stiffness is typically a function of the content percentage, whether it's short glass or other fillers, but you will see higher stiffness when using long fiber reinforced materials. Also, we can add design characteristics like ribs and gussets to further improve the stiffness. Strength is again a function of content percentage, but you will see higher strength with long fiber materials in the final parts. Also, we look at part design and mold design to optimize those for alignment and orientation in the final part, with the goal to be aligning those perpendicular to high stress areas, which again will increase the performance in the final parts. And the final area that we're looking at is toughness, and this is where long fibers outmatch all the competitive reinforcements. With long fiber materials, you get high stiffness and strength, but you also get high impact properties. And I'll show you why in a couple of slides. But again, unmatched impact properties in the final parts, and we see that toughness even at cold temperature impact, or at cold temperatures. So here's a graphical representation of what we've been just talking about. Over on the left, we have a performance level, and on the bottom, we have fiber length. And as you can see, as you move to the right, we get longer in the fiber length. As you start off on the side with the stiffness, you can see that stiffness goes up fairly quickly no matter what fiber length you start with. As we move towards the right and we get over 1 millimeter in fiber length and then beyond, we start to see increases in strength. And then as you go to the red line for toughness, you'll see that we need to really get into that fiber length of 7 to 8, upwards of 10 millimeters to get toughness. So again, this is where long fiber really shows its stripes. This slide is my favorite slide because it gives a visual representation of why long fiber materials have the properties that they do. On the left, we have the black part, which is a molded part of a nylon 6/6 with long glass, likely 50%, and the part on the right is a burn-off of that part, where we've essentially taken the resin and burned it away. And what you can see is left is a skeletal matrix. We've got some areas where there's high fiber orientation, and then we have other areas where those fibers are intertwined with each other. And it's this skeletal matrix that gives the high strength, stiffness, but also impact resistance. It's because now loads can be distributed across wider surface areas of the part. Another couple areas to note in this picture, or in this slide, is that if you look in the center, you can see those thin ribs. Well, those thin ribs, as you can see on the white part, is they're filled with glass. And that's because of that pultrusion process, where we're fully wetting out those fibers, protecting them during the molding process, and allowing them to get into thin sections. Along the perimeter of the part, you can see thicker sections near the screw bosses. And those thick sections are filled with glass as well, and because of the low consistent shrink, we don't see voids or warp in those areas. So now with long fibers, it gives designers flexibility in part design to moderate or change wall thicknesses from thin to thick. So what are some of the other benefits of long fiber? Specifically mass reduction or light weighting. The high strength to weight ratios with long fiber materials make it easy to displace traditional materials like metal. They're more robust, so in a lot of cases we can actually thin the wall stocks down and use less material, which again lends to light weighting. They have great cyclical fatigue endurance, and they also have very good dimensional stability because of the low and consistent shrink. They have better creep resistance, and they minimize sink and warp in heavy sections. So when we take a look at those properties, they make them ideal for metal substitution. The high strength to weight ratio combined with the injection molding process lead to an economical way to replace metals. What we find in talking with engineers and customers is that they choose metals because they're familiar with them. And a lot of times they're often overspecified. When we look at thermoplastic composites, we have to look beyond cost per pound or cost per kg. We have to look at the entire system's cost. We have to couple in the fact that if we use injection molding, we can combine parts into single parts. We have flexibility there to integrate design features, and we can reduce and eliminate secondary operations, reducing the overall systems costs. As we kind of talked about on the previous slide, plastics provide design freedom where we can use complex geometries and give more complex design and put some flexibility into those designs. Along with thermoplastics, you get corrosion resistance and also electrical and thermal insulation. I should note that if we are using carbon as a reinforcement, which we'll talk about in a little bit, the materials will actually be conductive and not electrically insulation. So let's talk about long glass fiber composites. Long glass PP, or polypropylene, has been used significantly in structural or semi-structural components in the automotive industry for over 30 years. Glass is a strong yet flexible fiber, so you get stiffness and strength, but you also get toughness and impact resistance. This is true for the stiffness and strength at higher temperatures, so we get higher heat deflection temperatures under load, and it's fully colorable. So this is a spider graph comparing nylon 6/6 unfilled to short glass, long glass grades. And if you look, I'd like you to look at the blue line, which is signifying a 50% long glass PA66. And as you can see, it has the best balance of performance, whether it comes to strength, stiffness, and then impact resistance when compared to short glass materials. And the graph on the top here is just comparing short glass nylon to long glass nylon at different percentages. And where I want you to focus your time is over to the right, where we're looking at long glass materials. You can see over the right that they have the highest impact resistance, or notch diazide impact resistance, and also the highest strength. If we look into the bottom right-hand corner, we're comparing some of our long glass materials to metals, lightweighting metals, specifically magnesium and aluminum, and you can see our impact resistance is higher than those metal materials. So now let's switch gears and talk about long carbon fiber reinforced composites. Carbon fiber is synonymous with high performance. It's the pinnacle of performance in injection molded plastics. Carbon fiber is 30% lighter than glass composites and 50% lighter than aluminum. And the graph at the bottom is doing some comparisons where we're comparing long glass over on the far left. We'll look at 60% reinforced to 30% long carbon reinforced nylon 6/6. As you can see, even at the lower loadings, we have higher strength, and that also helps with the lower density to reduce weight. Carbon fiber has been widely adopted in high-performance aerospace, defense, and sports and rec applications. It has a high-tech, sexy perception, which gives it a marketing advantage over other reinforcement types with consumers. The one negative on the carbon fiber is that it can be a higher cost reinforcement. And that's why, again, we have to look at that higher systems cost, we have to look at the systems cost versus cost per pound or cost per kg. Conductive materials, carbon fiber does make thermoplastics conductive, so they can be used in EMI shielding or anti-stat type applications. And here's some graphical representations of the strength and impact resistance of common reinforced materials, specifically long carbon versus short. And again, if you look over to the right, we're looking at 30 and 40 and 50% long carbon reinforced grades. They have highest strength of these different materials, and they also maintain or have higher impact properties. I will note if you compare the notch diazide, we're in the 4 to 4.5 range. This is lower than long glass materials. And that's because of that ductility or flexibility of the glass that we talked about earlier. If you look in the bottom right-hand corner, we're comparing long carbon fiber grades versus some common metals. And as you can see, with carbon fiber reinforced thermoplastics, we actually have higher strength than aluminum and magnesium, and we match up nicely versus stainless steel and titanium. So now let's talk a little bit how we can further tailor the composite materials to meet application requirements. Again, as we said earlier in the presentation, we can use any thermoplastic resin, anything from a polypropylene commodity type resin up through engineering resins like nylon or polycarbonate, all the way up to high-performance materials like PEEK or polyether imide. We can use any or many different fiber types. We've talked about glass and carbon, but we also have basalt fiber, and aramid fiber, and stainless steel. Aramid would be used in applications where you need wear resistance, and stainless steel where you need high conductivity. And then we can also add things like lubricants and flame retardants and colors as well to further tailor the material to the application. So let's talk about a few more specific products. First would be our hybrid glass and carbon material. This is actually where we put glass and carbon in a single pellet solution. What you get is a balance of property performance of the glass and carbon, carbon bringing stiffness and strength, and glass bringing that toughness aspect. Additionally, now with adding glass to carbon, we can balance out the cost as well. And as you can see, if you see the pellets up on the top right, the white portion would be the glass and the black would be the carbon. And now we can also tailor the overall reinforcement level, or the amount of reinforcement, and the ratio of carbon to glass to meet the application requirements. This slide shows how a hybrid reinforcement or reinforced material compares to a long glass and a long carbon material. In this case, we're using 20% long glass and a 20% long carbon hybrid material. And if you look over on the left in the impact resistance, when you compare that to a 40% glass material, we actually have 78% of the impact resistance, and we get 125% performance boost over carbon fiber. And when we look at strength, we get 124% of glass fiber, and we maintain 96% of the strength of a straight carbon fiber reinforced material. From a stiffness, you can see there's a huge increase in stiffness with the addition of the carbon, but we maintain about 87% of the carbon fiber stiffness with a hybrid formulation. So with a 50% reduction in carbon fiber content, we can actually reduce the cost of the material by about 40% as well. Another grade is one of our maximum toughness grades, and this is a grade that we position in materials or in applications where they need high impact. A couple of points on this is that we get about a 40% increase in notch dies-out impact over standard long fiber thermoplastic materials, and we actually get about a 400% increase in toughness versus short fiber compounds. We get all this while maintaining the same stiffness and strength of the long fiber materials. And here's some impact data in comparison. Long glass MT products over on the far right on the top graph, and then on the bottom we're looking at carbon fiber. But as you can see, by the addition of the MT product, we get significantly higher impact values, and then that both is true in the glass formulations as well as the carbon formulations. One other product that we'd like to talk about is our Velocity product. And this is a product that is used in applications that need high or very good surface appearance. Typically, you get better surface appearance with long glass materials or long fiber materials than you do with short fiber materials. And that's because there's less fiber ends in those products. But if you need to further improve it, we can go to a Velocity grade, which is a higher flow grade. It can increase flow lengths by 30%, cut injection pressures by as much as 40%, and may allow you to lower molding temperatures, which can reduce cycle times by 25%. If you look over on the right, the bottom right-hand corner is our Velocity grade at the same processing conditions compared to standard long glass materials, and you can see there's a big improvement in surface appearance with this product. One other unique product that I'd like to highlight is our thermoplastic polyurethane, and this is a translucent grade, where we can load the material with 20 to 50% of glass reinforcement, get a structural type material, but also have it translucent. So we can have it in components where you want to reveal internal components, such as housings, monitoring windows for fluid levels, and in some applications, LED backlighting. So again, we can incorporate multifunctional performance through the addition of additives like flame retardant agents and lubricants for wear resistance on top of our long fiber thermoplastic materials. So let's talk a little bit about PlastiComp. We're different than other material suppliers. Not only do we provide the material solution, but we also partner with our customers and our engineers to take it from design concept all the way from formulation through FEA analysis and mold filling analysis to prove out concept, and then in some cases prototyping and actually production. So as other companies may be not adding resources, we do add resources to try to help and support our customers. And again, when we look at developing applications with our customers, we look at this approach where we work with part design, injection molding, or different conversion processes, and the fiber technology to really give our customers a solution that will work in their application. So now, I'd like to summarize that we have, what we've talked about is long fiber composites are the best plastic option for metal replacement. They typically have the highest level of structural performance available in thermoplastic materials. PlastiComp has a wide portfolio of solutions tailorable to your performance and design requirements. And yet, we allow for a single supplier capability to support you and your concept through production.